Hello, welcome. I'm glad you chose to watch this session. My name is Hong. I'm a product engineer on Team Raster. I'm going to talk about creating orthoimagery from aerial and satellite imagery using ArcGIS Pro. I'll start with this slide to give you an overview of the extensive image capabilities of ArcGIS, from content, image management, analysis, visualization, to map production. ArcGIS map production include a variety of tools to generate products such as elevation, orthomosaics, and meshes. So our session will focus on using ArcGIS Pro to create auto products. In this presentation, we'll first go over the Pro auto mapping capabilities, then we'll demonstrate the workflow of processing satellite imagery, aerial imagery, and drone image. Through these demonstrations, you will learn not only how to create auto mapping workspace for different data types, but also learn the different ways to handle things like ground control points, ways of creating auto mosaics, and so on. Auto mapping is a process that corrects geometric distortions in the imagery to produce auto image products that can be used in mapping and GIS applications. With Pro Auto Mapping, you can process 4 types of imagery: satellite, aerial, drone, and scan imagery, and produce digital surface model and a digital terrain model, which is the bare earth elevation, and also orthomosaics. Auto mapping process is a computational intensive process: type point matching, triangulation, point cloud generation, and so on. The good thing is that Pro Auto Mapping supports parallel processing. With a regular machine of 8-core 16 gig memory, you can process hundreds and thousands of images. A machine of more cores or more memory will reduce processing time. We streamline the process into 3 steps: create workspace, which organizes the input and output into Pro project. The user experience for creating workspace from the 4 data types are different, but once created, the rest steps are same. So the second step is perform adjustment, which includes type point matching and triangulation. The third step is generate products. Pro Auto Mapping user experience is built on top of GP tools. You can automate with GP model or Python if you need to. But just to be aware that you cannot automate everything because you will need some manual work to use ground control points. For satellite imagery, auto mapping process image with RPC camera model, such as World View, GeoEye, Iconos, etc. We support 32 sensor types out of box. Processing satellite data requires an initial elevation data. We strongly suggest that you use a local DEM for processing satellite imagery. If you don't have, you can download ArcGIS raster data setup, which comes with a 180-meter resolution global DEM. Optionally, you can export a portion of the DEM from the elevation service from ArcGIS Online. This will avoid letting auto mapping engine to deal with the network. Some users might want to process pen-sharpened images. The workflow is similar, just choose a pen-sharpened processing template during workspace creation. For mixed sensors, not recommended, but if you must process data from different sensors due to data availability, what you can do is to create a mosaic dataset first, then add data from different sensors to the mosaic dataset and create satellite workspace from the mosaic dataset. The first demo is processing satellite imagery. The input is 16 ZY3 images taken with a 3-line camera with neither forward and backward view. The data will have very good overlap for DEM generation. We have also georeference image chips for ground reference, and also a 90-meter DM. We will generate a 10-meter digital terrain model and also orthomosaic out of those. This is a pro project, and this folder contains 16 ZY3 images that we want to process. I'm going to bring up the workspace wizard and to create a satellite workspace. Define the name and the workspace type. And the sensor type is ZY3 SysMac. Set the input data and specify the spatial reference. This will be used as the spatial reference and the VCS for the output product. For satellite data, we should use a local DM. If you don't have local DM, you can install ArcGIS raster data setup that contains a 100-meter resolution global DM. For processing template, I can use the 3-line stereo so that it will include native, forward, and backward images. And go ahead to create. Now the workspace is created. In the catalog pane, there is a auto mapping folder, and the workspace is here. Product folder will hold the output products, and the image folder contains the mosaic dataset that reference the input images. We can open the footprint table of the mosaic layer, and these are the images that we've just added. The images are mosaicked on the fly. We can look at the accuracy of the before the adjustment, and we see some misalignment between two tracks. So the first step, we want to perform adjust. Here you can see that there's a button reset, which is new at Pro 2.6. You can roll back a processing stage. And adjust include type point adjustment and block adjustment. So we'll go ahead and run. So now it's finished. We can look at the result at these two bookmarks. It has been improved, but not perfect. We can check at another location. This location is a little bit better. To further refine the adjustment, I want to include ground control point and then compute digital elevation model. For this dataset, I've received some georeferenced image chips that I want to use those as the reference. And I had made a mosaic dataset out of those image chips. We can look at alignment before adjust. There is a small shift. And then check out at another location. At this location, it is better. And because actually we already applied a 90-meter resolution elevation data to the mosaic dataset. So I can measure ground control point, but in this demo, I want to compute using the reference image chips. This message is a reminder that we should use a good reference in terms of both geometric accuracy and resolution. My reference data is good. And I set the elevation source for extracting Z value and enable geoid option, as the Z for satellite data requires an ellipsoidal height. And then go ahead to compute. Now we have the points computed. Let's zoom in to check the accuracy. Bring up the GCP manager, and I can use this filter tool, filter based on the current display, and compare the ground control point and the type point. Yeah, it is the same point, which is good. And now I can go ahead to adjust, which will use the updated points in the control point table. So we review the adjustment report. The error is very small, and the ground control point deviation also meet the requirement of our processing requirement. So next step is to generate the digital elevation model using the digital DEM wizard. And I use SGM method and set 40 as the object size to filter digital terrain model because I want to generate a digital terrain model. Set the output size, cell size, and go ahead to generate. And now the elevation digital terrain model is generated. Very nice, very beautiful digital terrain model. And now I'm going to use this to generate orthomosaic. And to do so, I bring up the orthomosaic wizard, set the elevation source to auto-rectify the image, and perform color balancing, and use disparity to method to compute the seam line, and just generate orthomosaic in the source resolution. And here is the orthomosaic that we generated. We can check the accuracy at the bookmarks we have saved. It is perfectly matched. And another location, which is very good as well. We can look at the seam line mosaicing result across the seam line, which is very good, mosaiced very well. So with Pro Auto Mapping, we have generated a auto-rectified mosaic dataset and a orthomosaic in CRF and a digital terrain model. Next, we'll look at the aerial digital workflow. The digital aerial image processing in Pro is designed for images with orientation. These images are typically captured with professional photogrammetry cameras that have IMU component. If your data do not have orientations or have very poor orientations, you can use drone workflow to process. Some users once struggled with preparing X-ray frame table and X-ray camera table. But I just want to point out that you don't have to because we have user experience letting you to input the camera parameters and create workspace directly from exterior orientation table. I'll show this in the demo. In the demo, we'll use 14 images over St. Clair River by Detroit, taken by Trumbull Aplanix camera. The input data includes exterior orientation table, a camera file, and also the GCP points that I collected from NAP Imagery. Purely for this demonstration, we want to create an Orthoimagery out of those. Here is the input table that has exterior information, XYZ, omega phi kappa, and name, and also the camera information that is prepared from a calibration report. I'm going to create a workspace to process these aerial images. So I bring up the workspace wizard, give the name of the workspace, and the workspace type is aerial digital, and set the input exterior orientation table. Since the field do not match the frame camera schema, we are given this UI to do the field mapping. Define the input, the space reference for the input images, and define the field for perspective X, Y, and Z. And use the sample data to verify the input is good. And for camera, I can input the file that I had prepared. And then you can also type in the camera parameters from here. Next, define the elevation for the study area. I'll let the system to extract elevation values from the service. You can also type in a constant value if you don't have access to the web, and go ahead to create a workspace. The initial georeferencing of this block is very good, and we see small shift between two images along two different flight lines. I can go ahead to adjust using the Adjust tool. It will include type point matching and block adjustment. Since the workspace uses a mosaic dataset to manage the data and process, it will display the process result on the fly. So as you can see, the shift is already gone after adjustment. So next step is to refine adjustment using ground control point. I had measured the ground control point from the reference NAIP image, and now I can go ahead and import it. This is the file, and define the space reference for the ground control point. And make sure the names, the fields are good, and go ahead to import. I can turn on the NAIP layer so that I know where those ground control points are. And can now start to measure the type points for each ground control points. I measure the type points at one image, and the second image is automatically calculated. I had to measure the third one. For the second ground control point, I'll do similar thing and measure type points. And now I have measured all the type points and go ahead to compute adjustment using the updated control point table. Let me generate adjustment report. 017 representation error is very good. And let's see the adjustment result on ground control point. We have small error on ground control point and also on checkpoints. So if you look at on map, we still have bigger shift because at this point the mosaic dataset hasn't been auto-rectified yet. So I'm going to use the custom wizard and auto-rectify the mosaic dataset and skip the generate output at this point. And go ahead. I'll auto-rectify using an external elevation data that I had outputted from elevation service. I'll do color balancing and also simulate generation and go ahead. As you can see, when the elevation data is applied, the image is already updated. We can check at another location, and we also have very good result on this checkpoint. Further look at the similar mosaicing. At a location we had seen before, yes, we have very good result at this as well. So next, I'll just go ahead, skip all the steps that I had done and generate final auto mosaic at the source resolution. So now I have the auto mosaic. So this is the workflow of processing aerial images. We've showed you how to create a workspace from an exterior orientation table, how to import ground control points, and measure type points, and finally auto-rectify using an external DEM. The third data type we'll process is drone. Drone images are essentially aerial images with the GPS of low accuracy and no orientation. We support JPEG and TIFF format with EXIF header. We also support external GPS data. If you have GPS data stored in a text file, we can read it as well. Because drone images do not have orientation information, the processing will be slightly different from traditional photogrammetry processing. It first estimates image orientation at a coarse resolution and then perform adjustment at full resolution. With ArcGIS Pro, you can process red edge and autumn images. We handle band alignment during adjustment time. At Pro 2.6, we support red edge reflectance panel, so we can process images and produce surface reflectance mosaic and create high-quality index map. Another feature we've added in Pro 2.6 is the capability of processing images with high-quality GPS, such as RTK and PPK. The adjustment will fix the image locations and only adjust image orientations. With high-quality GPS data, you can skip ground control point measurement, which really simplifies the workflow. Let's do a quick demo. The input is simple, 21 JPEG images. Since previous two demos have given you the whole picture of the auto mapping workflow, for this particular demo, we'll just focus on workspace creation, then we'll generate DSM, then measure volume, show you how to measure volume. To process drone images, we create a workspace of drone type, give a name, drone is the default workspace, and add data from a folder. Here now in the list, this is the image preview and also the GPS data from EXIF header. The camera is automatically defined based on our database, camera database. If you have a new camera, which we don't have yet, then you can type in the focal length and the pixel information. The projection is also automatically defined based on the GPS data. We automatically calculate a UTM from the GPS data. Now we go ahead, create a workspace. Let me turn off the flight path. Similar as other data types, we'll process using adjust tool. For drone though, you will see the options are different because processing drone images involves two steps. First, estimating orientation using a coarse resolution data, and then perform adjustment at full resolution. You can do a quick adjust only by enabling the first option, but in our demo, we'll do full adjustment. I'll go ahead to run. I use the same workflow that I showed you earlier and have adjusted with GCP and now ready to generate DSM. I'll use SGM method and I'll set output is DSM and go ahead to generate. I can visualize the DSM using a hillsheet function. Turn off the layers. And bring up the volume tool. And start to measure. Set the current layer to be the right one. And I draw a polygon around this pile. So the volume is automatically calculated, and I can measure another one. So I can save this as a report. So this is how simple you can process drone images, produce DSM, and measure volume. To summarize, we had showed 3 demos. We first processed ZY3 satellite images and went through the whole workflow and produced digital terrain model and orthomosaic product. Then we processed aerial images. We showed how you can create workspace directly from exterior orientation table. We measured ground control points and created orthomosaic by auto-rectifying with an external DM. For drone workflow, we showed how to process drone easily and how to measure the volume using digital elevation model. Some additional resources here. Make sure you check out these sessions available at Virtual UC. There is a presentation which gives you an overview of the mapping product capability in ArcGIS. If you want to know how to process scanned images, there's an on-demand session for you. The processing drone with AutoMaker shows you how to process drone with Enterprise. There are also some general imagery and remote sensing resources available to support you if you work with imagery and RAS data. Please be sure to visit us at the Virtual S3 Showcase. Thank you for watching.